Norton equivalent circuit. Similar to Thevenin equivalent, Norton equivalent circuit is the equivalent of a circuit which contains linear components such as resistors, voltage and current sources, dependent or independent sources. Okay, but it shouldn't contain non-linear components such as diodes. Okay. 2 points from that circuit, if you look at 2 points from that circuit, you can find a Thevenin, a Norton current between these 2 points, and you can find a Norton resistance between these 2 points, and you can find a Norton's equivalent for the circuit. Okay, and then you can connect any component. This component can be linear or non-linear, it's not important. If you connect the component here, okay, like that, or if you connect the same component here, it will not understand any difference. Okay, it will behave like it's not changed. Okay, it will have the same voltage, it will have the same current, so voltage of X, current of X, or power of X will not change. So it's important to find the proper Norton current and Norton resistance. So what you do is to calculate 2 values. Okay, values of the circuit. You have to calculate what's the I Norton and R Norton of that circuit. To calculate I Norton, what you do is this: you connect these 2 cables, these 2 points with a cable, and then you calculate the current, or if you have a real circuit, you measure the current. That current is I Norton. That's it. Okay, the value of that current will be the value of I Norton. I Norton. A prime and B prime. Okay, so it's not very difficult. Similarly, to calculate R Norton is very easy. To calculate R Norton, what you should do is this: turn independent sources off and measure the resistance between points A and B. Okay, that's the R Norton, and that's the equal value for R Thevenin. Okay, R Thevenin and R Norton are the same values. In the Thevenin equivalent model, you will measure the Thevenin resistance similarly. So let's apply on a circuit. Yes, let's calculate the voltage of I source 2, current source 2, and I will use the Norton equivalent circuits of the remaining parts. Okay, if you try to find the value of some component, you have to reject that component and calculate the equivalent of remainings. Okay, if you include that component, it will be eliminated. You cannot calculate V source 2. So you have to reject that component. What I mean is this: you will take this circuit before analysis. Okay, if you calculate the equivalent of these points, okay, it will be wrong. You have to reject that component. You have to reject that component like that. Okay, and then you will find a Norton's equivalent for this circuit: A prime, B prime, I Norton, R Norton. Okay. Then, after calculating the equivalent, you will insert the component here, like that. Okay. So, let's calculate. This is our circuit whose Norton's equivalent will be calculated. Calculate I Norton. For this, I will short points A and B, and I will calculate this current. This current will be equal to I Norton. What's that current? How can I calculate? This current is the current of this resistor, isn't it? I have to calculate the current of that resistor. For this purpose, I can calculate the voltage of this point. Okay, and then let me say this is 0, ground. If I calculate current, if I calculate voltage E, I Norton will be E divided by R3. Okay. How can I calculate the voltage of point E? To calculate voltage of point E, I will apply combination rules. These two are connected in parallel. Let's redraw the circuit. This is point E. This is R2 parallel R3. This is R1. This is V source 1. So this is ground. What's the voltage E? Voltage E is voltage of these components. Okay, voltage VE, let me say. Okay, which is equal to one voltage source. Voltage is divided on two resistors. Total voltage times the resistance divided by summation plus R1. That's E. So what was I Norton? I Norton is E divided by R3, which is equal to E divided by R3. Okay. So this is I Norton. Calculate R Norton. Let me take my circuit. Okay. To calculate R Norton, all sources they should be off. Okay, all sources should be turned off. What does it mean? Turn off a voltage source. It means 0 volt. It means short circuit. If you turn off a current source, it means 0 current which means an open circuit. Here there is 0 volt, here there is 0 current. Okay, so my circuit, let me turn the sources in my circuit. There is a voltage source. I am replacing it with a short circuit. Now the resistance that I will read from port AB, point AB, will be the Norton's resistance. So if you look at from AB, what's the resistance, total resistance? How are these connected? They are connected in parallel. So let me redraw my circuit. This is R3, A, B, and this is the combination R3 parallel R1, sorry, R1 parallel with R2, and the resistance that I will read will be the Norton's resistance. How are these connected? They are in series. So let me redraw my circuit. Total resistance is summation, which is equal to R3 plus R1 parallel R2. These points are A prime, B prime, A prime, B prime. Okay. So what's my Norton resistance? R3 plus R1 parallel with R2. The parallel connection has the higher precedence. If you see something like that, you will calculate the parallel value first. Okay, it has the higher precedence, so you don't have to put a parenthesis like that. When you see parallel connection, you will do it first and then in series connection. So let's draw the Norton equivalent. Norton resistance, this is A prime, B prime, R3 plus R1 parallel R2. What was I Norton? I Norton is this. Okay, I Norton. So this is the equivalent of my circuit. And then what was the question? Question is to calculate VS2, voltage of this component. I have rejected that component. Then I have calculated the Norton's equivalent of the remaining part. Now I will insert the component to make analysis. Okay, connect like that. VS2 is the voltage of this resistor. Can you see? Voltage of a resistor is equal to resistance times the current. What's the resistance? R3 plus R1 parallel to R2 times the current. What's the current? This current, let me say I1. This current, let me say I2. What's that current? I1 plus I2. Okay, that's the value. Now let's have a numeric example on this example. Let me copy my circuits and give some values and calculate. Okay, let's find the value of VS2 using Norton's equivalent of the remaining parts. So first I will copy the remaining parts except the current source, and then I will calculate a Norton's equivalent for this part, I Norton, R Norton, and I will connect these components to here. Okay, I will connect like that and then calculate the voltage. So let's calculate I Norton. I Norton is the current of short circuits, points A and B. What's that current? I Norton. How can I calculate? After finding the voltage of this point, I can calculate. Okay? First, how are these connected? They are connected in parallel. Let me redraw the circuit. 4 volts. 5 and 6. Equivalent resistance is divided by summation, and which is equal to 2.72 ohms. What's the voltage of E? If you say this is ground, this voltage will be equal to E. Okay? And by voltage division, voltage of this resistor is total voltage times the resistance of the voltage divided by total resistance, which is equal to, which is approximately 1.2 volts. Okay, so if this voltage is 1.2 volts, what is this current? Here is ground. E minus 0 divided by 5. Okay, I Norton is the current of this resistor, and the current of that resistor is voltage divided by resistance. So I Norton is, look at the circuit again, E minus 0 divided by 5 ohm, which is equal to 1.2 divided by 5. 0.24 amps. Okay, so as you see, it's very easy. Now the next step is to calculate the Norton's resistance. To calculate R Norton, turn all independent sources off. This is my circuit. There is a voltage source. If I turn the voltage source off, it will be a short circuit like that. And now, what's the resistance we read from the points A, B? These two are connected in parallel. If I redraw my circuit, it will be like that. This is 5. 4 times 6 divided by 10, which is 2.4 ohms. So total resistance will be, our Norton will be, they are in series, 5 plus 2.4, 7 plus 7.4 ohms. That's it. Okay, let's draw the equivalent model. Resistance is 7.4 ohms. Current is 0.24 amps. And now these are points A prime, B prime. Now I can put the source here and then calculate the voltage. Okay. So the voltage of this source Vs2 is the voltage of this resistor. They are connected in parallel. Is it obvious? So Vs2 is equal to Vr, which is equal to resistance times the current entering from the positive terminal. Resistance is 7.4. The total current is I1 plus I2 plus 7. Okay, which is equal to times 7.24, 50.68 volts. That's it.